Hi, this is Mrs. Vrobel. This is part 2 of covalent bonding. So in the first video you were watching, we were talking about covalent bonds and how to identify them as opposed to ionic bonds. We also talked about polar covalent bonds. So if we see a difference in electronegativity, how does that change the sharing of electrons that goes on between two atoms? And then today we're going to look at valence electron pair repulsion theory. And before we start talking about that, I thought I'd show you a couple of friends that I brought from Oaxaca. So here I have two magnets. And if you take two magnets and you put their ends together, what happens? So you might notice that you get some repulsion going on. And depending on how strong the magnet is, some repulse better than others. But notice that if the direction of the polarization of the magnet is the same and you bring those two sides together, you get a repulsion. Well, that's similar to what we witness with electron pairs. So when we're looking at electron pair repulsion, the electrons that are surrounding the atom, they actually cause the atoms to move in certain directions. And we notice that they have an angular separation. So there's three different types of sharing that we witness with covalent bonds. So we could have 4 electron pairs, and these electron pairs are essentially shared between a number of atoms, and they form what we call a tetrahedral. So we will look at shapes of molecules in this section of the chapter. We could have covalent bonds that are sharing 3 sets of electron pairs, and they tend to form a sp2 hybrid, and their shape is trigonal planar. And then lastly, we could have 2 electron pairs, and they form an sp shape, which is linear. And we will get into more detail about what those shapes look like. So here are 3 different types of bond angles between covalent bonds. So notice that water, and you need to pay attention to these purple lobes. These are lone pairs of electrons. And in this section of the chapter, it's very important to understand or to observe where you see lone pair of electrons. Notice that the angle is the smallest. And because there are 2 pairs of lone pair of electrons, they actually push the hydrogen bonds down further, creating a very small bond. Now, where we have 1 electron pair, notice that the bond angle actually increases. So we have more freedom of movement. The hydrogen aren't pushed down as much as they are with water. And then lastly, we have no hydrogen. We have no lone pair of electrons, and we get the greatest degree of separation. So what this is telling you is that the more lone pair electrons you have, the more repulsion you have, and the more limiting of the bond angles you have because of that. Now, when we look at strength of covalent bonds, we actually find that as you increase the distance between molecules, you actually get a loss of covalent bond strength. Okay, so as you increase length, you decrease strength. Also notice that when you go from single to double to triple, your bond length actually gets shorter. So that's going to tell us something about bond strength too. Now, you're going to find when you want to do a chemical reaction, you really do care about bond strength because we have what we call bond dissociation. So we're essentially trying to break up that covalent bond and maybe reform other bonds. And if that bond is really strong, it's going to be difficult, maybe impossible, to break up that covalent bond and create a new molecule. So covalent bond strength is very important for us. And notice that for fluorine, its bond dissociation energy is significantly smaller than nitrogen. And the interesting thing is nitrogen, we're actually talking about a triple bond. So we have 3 covalent bonds overlapping with each other, and it's sort of like reinforcing that covalent bond structure so that we get a high dissociation energy. Okay. You will notice that endothermic reactions, so reactions that take up energy, hopefully I do some demonstrations with you in the class where you can see an endothermic reaction. And notice that with endothermic reactions, we have to put in energy to break up the bonds in the reactants to get products. So it's not an easy reaction to do necessarily. Exothermic, you actually get heat production within the product. So you may notice that when you're making something, if the pot gets warmer, okay? And we're not talking about heating the pot, but we're talking about the reaction in the pot actually making it warmer. That would be an exothermic reaction. So there's actually stored energy in the reactant that gets released when you form the product because there's an excess of energy. Okay, before we wrap things up, I just want to talk about 3 types of bonds, and this is somewhat of a review for us. So all this chapter we've been talking about covalent bonds. So we notice with covalent bonds, we see a lot of covalent bonds between hydrogen and a nonmetal. So if you see hydrogen with carbon or sulfur or phosphorus, it's a good chance that we're talking about a covalent bond. Now for polar covalent bonds, a good rule of thumb is you may see a metalloid. Remember, a metalloid is in that step stair of the periodic table, and it'll be combined with nonmetals. So the nonmetals are in the upper right-hand corner. Now, this is just a review, and this is something that catches students all the time. Remember, we're looking for the presence of metals. If metals are in the chemical formula, it's not going to be a covalent bond. It's going to be an ionic bond.